Welcome everyone, my name is Tatiana and this is my video series on OTF Studio thin film software. OTF Studio is a very powerful, smart and extremely fast tool for multi-layer design, thin film characterization, reverse engineering and monitoring of optical coatings. In my previous video, I demonstrated several OTF Studio tools for designing dispersive mirrors in the visible and near-infrared spectral ranges. You can find the link in the video description. In this video, I'd like to focus on the design of dispersive mirrors for the mid-infrared spectral range. Modern laser applications rely on broadband dispersive mirrors with high reflectance and a carefully tailored group delay shape. The shape controls the phase of ultrafast laser pulses. This schematic illustrates how dispersive mirrors operate. As a short pulse propagates through dispersive media, it accumulates group delay. In mid-infrared laser systems, pulses may travel through optical windows and crystals such as zinc selenide, germanium, zinc sulfide, and others. These materials introduce large dispersion. As a result, different spectral components of the pulse have different delays. The pulse broadens and its temporal shape may change. By introducing a dispersive mirror with an inverse group delay shape, we can compensate for the accumulated dispersion and compress the pulse to its original duration. Typical target specifications in mid-infrared dispersive mirrors are high reflectance, close to 100%, in a broadband spectral range, and group delay. The shape of group delay is important, and group delay variation is a key design parameter. The bandwidth of interest is typically expressed in optical octaves. In the current example, I will design a mid-infrared dispersive mirror for the range 612 micron that corresponds to the bandwidth of one optical octave. This is quite challenging. The mirror must compensate group delay in 1 mm zinc selenide. That corresponds to group delay variation of about 110 femtosecond. And for such challenging design task, I will take high contrast layer materials with high contrast of refractive indexes. I will take germanium and ytterbium fluoride, which provide high contrast of refractive indexes. On our website, you can find some theoretical estimations useful for designing of mid-infrared dispersive mirrors, based on your specifications, bandwidth, and materials. And these estimations predict that the total thickness expected is 12-13 micrometer, and average thicknesses of germanium layers are 0.5 micrometer, and for ytterbium fluoride 1.2-1.3 micrometer. I open my OTF Studio project configured for this design task. I have switched to micrometer units for spectral range and specified 100% target reflectance for the entire spectral range. And this is my model pulse in the range 612 micron, and group delay that must be compensated. This is group delay accumulated in 1 mm zinc selenide. And the target group delay has an inverse shape. Dispersive mirrors are defined by relative group delay, not absolute group delay. The target group delay is not uniquely defined. Only its shape is important, not its absolute value. This means that a constant group delay shift does not change pulse compression. If we shift the target group delay by an arbitrary constant, it will simply mean a time-axis shift of the pulse and does not affect the pulse shape. It's possible to relax target requirements using so-called floating constants. In this example, I used floating constants in the target, and floating constants enables you not to require that the group delay to be fixed in absolute values, but relax target requirements. In the visible and near-infrared ranges, substrates and crystals such as fused silica, optical glasses, and aluminum oxide usually have a group delay that decreases with wavelengths. In contrast, for most mid-infrared windows and crystals, the group delay increases with wavelengths. This difference affects the structure of dispersive mirrors. For visible and near-infrared dispersive mirrors, a typical starting design is a chirp mirror with layer thicknesses that decrease with layer number, and for mid-infrared dispersive mirrors, the layer thicknesses typically increase with layer number. Select a starting design. This is a chirp mirror. I load this chirp mirror. It provides already high reflectance in the entire spectral range from 6 to 12 micron. Let's switch to design structure. This is a modulated quarter wave structure with quarter wave thicknesses from 0.7 to 1.3 and the central wavelength 8.6 micrometer. And it's interesting, you can see that the layer thicknesses increase with layer number, not decrease. I switch to the Design Builder panel and select Gradual Evolution with standard settings and the maximum number of layers 15. Start, and very fast we can obtain a 16-layer solution with high reflectance. Reflectance is higher than 99.5% in the entire spectral range, 1 octave, 612 micron, and excellent correspondence to the target group delay. Let's check the pulse, output intensity, and here we can see two pulses, the input pulse, this blue line, and orange line is intensity after interaction with the dispersive mirror. And we can zoom and see that the losses are negligible even for these challenging specifications. Let's have a look at the design structure. Theoretical estimations predicted that the average thickness of ytterbium fluoride layers is 1.2, 1.3 micron. This is exactly the case. And average thicknesses of germanium layers is 0.5 micron. It's also the case in design solutions. Total thickness predicted was 12-13 micron, and the obtained design solution has 12.8 micron. What can be a practical problem is the last layer of the design is a relatively thick ytterbium fluoride layer. For better environment and stability, it's a good idea to add a germanium capping layer. In one of my previous videos, I showed how to create a capping layer, a design with a capping layer. See the link in the video description. So I have prepared such design with capping layer, 30 nanometer of germanium as the last capping layer. We can see that reflectance is the same, it doesn't change, but the performance, group delay performance is much worse now. So the design must be optimized using a refinement with constraints. I switch to refinement with constraints, and there is a constraint for the last germanium layer, 30 nanometers, so it means 0.03 micrometer. Now I start optimization with constraints and very fast obtain a 15-layer solution with the last layer of germanium, 30 nanometer, excellent group delay performance, and high reflectance. Now I saved this design with capping layer and would like to compare performance with capping layer and without capping layer. So using compare designs feature, I simply check both designs, and we can see that there is negligible difference between group delay performance and also in reflectance performance. Reflectance is high for both cases. But let's check the pulse analysis. And here we can see the output pulse, the pulse after interaction with this dispersive mirror design. And the losses are negligible. Merit function difference is negligible. So the design is not changed, and it has excellent spectral performance, and it's practical. I demonstrated how to compensate group delay variation of 100 femtosecond caused by 1 millimeter zinc selenide window. But what happens if we need to compensate not 1 millimeter of zinc selenide but 2 millimeter? The group delay variation is already 200 femtosecond in the broadband spectral range, or maybe we need to compensate more different substrates and crystals and windows. What if the required bandwidth and group delay variation cannot be achieved with one dispersive mirror? In many cases, this challenge can be solved with a dispersive mirror compressor. It uses several dispersive mirrors and provides 2, 4, 6, or 8 pulse reflections. In this case, the total target group delay is divided by the number of reflections, 2, 4, 6, or 8. The group delay and reflectance of a pulse compressor with n reflections or n bounces can be calculated as follows. The group delay is added for each reflection, while the reflectance is multiplied at each reflection. Of course, as the number of reflections or bounces n increases, the pulse loses some energy at each reflection. I move to my OTF Studio project and load another target for 2 millimeter zinc selenide. We can see that group delay that must be compensated is now 2 times larger. And of course, the mirror that was designed does not compensate this group delay. Let's switch to the pulse, output pulse, and as expected, we see that losses are very large because this is only one mirror. But what I can do, I can increase the number of bounces, not one mirror, but 2 mirrors or 2 bounces. And for 2 bounces, we can see that the pulse is now as before. There are losses, but only 1% for so large variation of group delay, about more than 200 femtosecond. As expected and predicted, the design solutions contain thick layers. One of them is thicker than 2 micron. I recommend again to have a look at theoretical predictions at our website. OTF Studio has various production-friendly tools and features that allows you to insert barrier layers or design compensating coatings for the backside. Thank you for watching. If you have questions, feel free to contact me and see you in the next video. Bye!